for your entire existence, you've been blind to 99% of what the universe is trying to show you. Until now. In March of this year, something extraordinary left our planet. A telescope unlike anything humanity has ever built. Its name is SPHEREx. And just 6 months after launch, it accomplished what no mission in history has achieved. It mapped the entire universe in 102 infrared colors. Every galaxy, every star, every cloud of cosmic dust, all captured in wavelengths invisible to human vision but absolutely dominant across the cosmos. Let me put this in perspective. When you look at the night sky, you see perhaps 3,000 stars with your naked eye. Your eyes detect 3 primary colors: red, green, and blue. That is the limit of human perception. But the universe does not speak in 3 colors. It speaks in hundreds. And for the first time ever, we have a translator. SPHEREx has given us the ability to see the universe as it actually exists, not as our biology allows us to perceive it. This is not just another space photograph. This is a decoded version of reality itself. Think about what that means. Every image you have ever seen of space, every breathtaking nebula, every spiral galaxy, those are beautiful, but they are also incomplete. They show you what light does when it bounces off objects and travels to your eyes. But what about the light you cannot see? What about the infrared radiation pouring out of star nurseries hidden behind walls of dust? What about the thermal signatures of planets forming around distant suns? What about the ancient light from galaxies so far away that their visible glow has faded into whispers? SPHEREx sees all of it, and here is the staggering part. It does not just capture one version of the sky. It captures 102 versions simultaneously. Imagine taking a photograph where every pixel contains not just one color value, but 102 separate measurements, each one telling you something different about temperature, composition, distance, and age. Each one revealing objects that were previously hidden behind veils of gas and dust. The telescope completed its first full sky map in just 6 months. 6 months to survey every direction in space, visible from Earth's orbit. 6 months to create a spectral fingerprint of the observable universe, and what it revealed is nothing short of mind-bending. When scientists processed the data, the sky transformed. In one wavelength they saw blue hues highlighting hot hydrogen gas, the raw fuel of star formation. Shift to another wavelength and suddenly red dominates, revealing cosmic dust scattered across galaxies like breadcrumbs marking the death of ancient stars. Move through more colors and you trace the distribution of stars and galaxies across cosmic time, watching structure emerge from chaos. But here is what makes this genuinely unprecedented. Every previous all-sky survey observed in maybe 1 or 2 wavelengths. Some missions mapped the sky in visible light, others used radio waves or X-rays. A few ventured into infrared, but only captured a handful of colors. SPHEREx obliterates those limits. 102 colors means 102 independent datasets. 102 ways to interrogate the universe about its secrets. And perhaps most revolutionary of all, this data is not locked away in institutional archives. It is publicly available. Right now, anyone with internet access can explore these maps. Citizen scientists, students, researchers from any country, they all have equal access to what might be the most comprehensive portrait of the universe ever created. Think about what becomes possible when you can see through dust. Star formation happens inside dense molecular clouds. These regions are opaque to visible light. Telescopes like Hubble cannot penetrate them, but in infrared, those clouds become transparent. SPHEREx can peer inside stellar nurseries and watch planets being born. It can trace the chemical ingredients necessary for life across thousands of light years. It can map the cosmic web, the large-scale structure connecting galaxies like neurons in a vast brain. This is not incremental progress. This is not a slightly better version of what came before. This is a fundamental expansion of human perception. For the first time, we have a complete infrared spectrum of everything in the sky, every patch of darkness between stars, every faint galaxy at the edge of detection, every wisp of interstellar matter drifting through the void. And we are just getting started. This is the first map, SPHEREx will complete 4 full all-sky surveys during its mission, each one building on the last, each one going deeper, seeing fainter objects, refining measurements. By the time this mission ends, we will have a data set so rich that scientists will spend decades mining it for discoveries. The universe just revealed its true colours, and nothing will ever look the same again. What SPHEREx has achieved, you need to understand how it pulled off this impossible feat. Because the technology behind this mission is not just impressive, it is fundamentally different from anything that has come before. And once you grasp how it works, you will realise why this telescope represents a genuine leap in our ability to decode the cosmos. Let me start with a question that should disturb you. Why have we been so blind for so long? We have launched hundreds of telescopes into space. We have built observatories on mountaintops and in deserts. We have invested billions in instruments designed to capture the universe in exquisite detail. And yet, until SPHEREx, we were missing most of the story. The reason is simple and profound. We have been looking at the universe in the wrong colours. Visible light, the light your eyes detect, represents less than 1% of the electromagnetic spectrum. Think about that. Everything you have ever seen with your own eyes, every sunset, every star, every colour that has ever entered your consciousness, that is drawn from a tiny sliver of reality. The universe does not care about human vision. It radiates energy across wavelengths we cannot perceive. And infrared light, the realm where SPHEREx operates, that is where the universe truly comes alive. Infrared radiation is heat. It is the glow of warm objects. And in space, warm objects tell you where the action is happening. Star formation is a messy, violent process. When clouds of gas collapse under their own gravity, they heat up. Dust grains swirl around newborn stars, absorbing visible light and re-emitting it as infrared. If you look at a stellar nursery with a normal telescope, you see darkness. Look at the same region in infrared, and it explodes with structure, glowing filaments, hot cores, the raw machinery of creation laid bare. But here is where SPHEREx becomes truly remarkable. It does not just observe infrared light, it dissects it. The mission uses a technique called spectroscopy, which means splitting light into its component wavelengths. Imagine holding a prism up to sunlight. White light separates into a rainbow. Red, orange, yellow, green, blue, violet. Each colour corresponds to a specific wavelength. Spectroscopy does the same thing, but with scientific precision. It breaks incoming light into hundreds of narrow bands, each one carrying unique information about the object emitting it. Now, most space telescopes use spectroscopy on individual targets. Point at a star, split its light, analyze the spectrum. Point at a galaxy, repeat the process. This approach works beautifully for detailed studies. But it is slow. You can only observe one object at a time. Mapping the entire sky this way would take centuries. SPHEREx takes a radically different approach. It performs spectroscopy on everything simultaneously. The entire sky. All at once, every single observation. Here is how it works. SPHEREx carries 6 detectors. Each detector is paired with a special filter. These are not ordinary filters. They are called linear variable filters, and they are technological marvels. Imagine a piece of glass where the colour changes continuously from one edge to the other. One side might filter out short infrared wavelengths. The other side filters out long wavelengths. In between, you get a smooth gradient covering 17 distinct infrared colours. Now multiply that by 6. 6 detectors, 6 filters, 17 wavelengths each. That gives you 102 separate colour measurements captured in every single image. One photograph from SPHEREx contains more spectral information than entire surveys from previous missions. And the telescope captures thousands of these images every day. Let me give you a sense of scale. Each image SPHEREx takes covers an area of sky as wide as 22 full moons placed side by side. That is enormous. Most space telescopes have narrow fields of view. They see tiny patches of sky in exquisite detail. SPHEREx does the opposite, wide field, massive spectral coverage, and by combining speed with breadth, It can map the entire observable universe in months rather than decades. Scientists have started calling SPHEREx the mantis shrimp of telescopes. And if you know anything about mantis shrimp, you will understand why that comparison is perfect. Mantis shrimp are marine creatures with the most complex eyes in the animal kingdom. Humans have 3 types of color receptors. Mantis shrimp have 16. They see colors we cannot even imagine. They perceive polarization, ultraviolet, and a rainbow of hues completely outside human experience. SPHEREx does the same thing for the cosmos. It sees what we cannot, and in doing so, it reveals a universe far richer and stranger than our biology prepared us to comprehend. But here is the key insight. More colors means more information, and more information means better answers to fundamental questions. When you observe an object in 102 wavelengths, you can determine its temperature, chemical composition, distance, age, and motion through space. You can distinguish between different types of stars. You can identify organic molecules in distant nebulae. You can trace the evolution of galaxies across billions of years, all from light, all from colors invisible to the human eye. And this is where the mission becomes genuinely groundbreaking. Dense dust clouds block visible light completely. Regions where stars and planets form remain hidden behind opaque veils. Hubble cannot see through them. Ground-based telescopes cannot penetrate them. But infrared light passes through dust like it is not even there. SPHEREx can peer into the hearts of stellar nurseries and watch the birth of solar systems in real time. It can track water ice, carbon dioxide, and organic molecules, the chemical ingredients necessary for life, as they drift through interstellar space and accumulate around forming planets. This is not abstract science. This is detective work on a cosmic scale. Every wavelength is a clue, every spectrum is a fingerprint, and SPHEREx is collecting evidence from hundreds of millions of objects scattered across 13.8 billion years of cosmic history. The telescope does not just take pictures, it measures, it quantifies, it transforms light into data and data into understanding. SPHEREx is not just mapping the universe as it appears today. It is building a 3-dimensional reconstruction of cosmic history itself, and in doing so, it is investigating one of the most profound questions ever asked. What happened in the first fraction of a second after the Big Bang? The answer lies hidden in patterns so vast they stretch across billions of light years, patterns that SPHEREx is revealing for the first time. Let me explain how this telescope actually builds its map. SPHEREx orbits Earth at an altitude where it completes 14.5 revolutions every single day. That is incredibly fast. Most satellites complete one orbit every 90 minutes or so, but SPHEREx uses this rapid motion strategically. As it circles our planet, it scans the sky in long strips from north to south, passing directly over Earth's poles. Each orbit captures a narrow slice of the cosmos. String those slices together, and you get a complete picture. Every day, SPHEREx captures approximately 3,600 images, 3,600 spectral snapshots, each containing 102 colors, each covering an area as wide as 22 full moons. The data volume is staggering, but here is the clever part. Earth itself is moving. Our planet orbits the Sun, and as months pass, Earth's position changes, allowing SPHEREx to see different portions of the sky. Over 6 months, Earth completes half an orbit, and in that time, SPHEREx gains access to every possible direction in space: north, south, east, west, every angle, every coordinate. The entire observable universe mapped in infrared spectroscopy. But this is where the mission transcends simple photography, because SPHEREx is not just recording where objects are, it is measuring how far away they are. Distance is everything in astronomy. When you know an object's distance, you know when the light left that object. Light travels at a fixed speed, 300,000 kilometers per second. Nothing in the universe moves faster. So when you look at a galaxy 1 billion light years away, you are seeing it as it existed 1 billion years ago. The light took that long to reach you. Astronomy is time travel. Every observation is a glimpse into the past. SPHEREx measures distances to hundreds of millions of galaxies, not thousands, not millions, hundreds of millions, and it does this using spectroscopy. Different types of galaxies emit light in characteristic patterns. By analysing these patterns across 102 wavelengths, scientists can determine how far away each galaxy is with remarkable precision. This transforms a two-dimensional map into a three-dimensional volume. You stop seeing galaxies scattered across the sky like points on a photograph. You start seeing them distributed through space and time like cities on a cosmic map. And here is where things get strange. When you map galaxies in 3 dimensions across vast distances, you notice something peculiar. They are not randomly scattered. They cluster. They form filaments, long chains of galaxies stretching hundreds of millions of light years. Vast walls of structure separated by enormous voids where almost nothing exists. The universe looks like a sponge, or a spider web, or the neural network inside a brain, patterns within patterns within patterns. These structures are not accidental. They are fossils. Fossils from the earliest moments of cosmic history. And this is where SPHEREx connects to the Big Bang itself. Specifically, to something called inflation. Inflation is one of the most important and bizarre ideas in modern cosmology. Here is the concept. In the first tiny fraction of a second after the Big Bang, the universe expanded exponentially. Not gradually, exponentially. It grew by a factor of 1 trillion trillion in less than a billionth of a trillionth of a trillionth of a second. Let me repeat that, because it sounds insane. The entire observable universe, everything we can see in any direction, all 100 billion galaxies, every star, every planet, every atom, all of it was once compressed into a region smaller than a single proton. And then, in less time than it takes light to cross an atomic nucleus, it exploded outward by a factor so large that numbers stop making sense. 1 trillion trillion times bigger. Instantly. This event is called inflation, and it happened so fast, so violently, that it left scars on the fabric of reality itself. Those scars are what SPHEREx is hunting. During inflation, tiny quantum fluctuations, random ripples in energy at subatomic scales, got stretched across cosmic distances. Imagine drawing dots on a deflated balloon and then inflating it to the size of Earth. Those dots spread out. They become separated by vast distances. The same thing happened to quantum fluctuations during inflation. Tiny random variations in energy density got blown up to galaxy-spanning scales, and those variations became the seeds of structure. Regions that were slightly denser attracted more matter. Over billions of years they collapsed into galaxies. Regions that were less dense became voids. The pattern of galaxy clustering we see today is a direct imprint of quantum fluctuations from the first instant of creation. Read that sentence again. The structure of the universe on the largest scales, the distribution of hundreds of billions of galaxies across tens of billions of light years, that structure was determined by random quantum events that occurred when the universe was smaller than an atom. That is what SPHEREx is mapping. That is what the mission is designed to reveal. Previous surveys mapped galaxies in 2 dimensions. They told you where objects appeared on the sky, but they could not tell you how those objects were distributed through space and time. SPHEREx changes everything. By measuring distances to hundreds of millions of galaxies, it constructs a 3-dimensional map of cosmic structure, and by analysing that structure, scientists can test theories of inflation. They can determine which models match reality. They can rule out ideas that do not fit the data. They can probe physics at energy scales so extreme that no particle accelerator on Earth will ever reach them. This is forensic cosmology. SPHEREx is investigating a crime scene 13.8 billion years old. The evidence is written in the arrangement of galaxies. The clues are encoded in patterns of clustering, and the story those clues tell is almost unbelievable. The universe we inhabit, with all its complexity and grandeur, emerged from a quantum fluctuation, a random blip in nothingness that got inflated into everything. SPHEREx is reading the universe like a history book, and the story it is revealing is stranger than any myth humanity has ever invented. Why does any of this actually matter? Not just to scientists, not just to academics, but to you, to humanity, to the future of our species, and the question of whether we are alone in this vast universe. The answer begins with three molecules: water ice, carbon dioxide, and organic compounds. These are not exotic substances. You interact with them every day. Water covers 70% of Earth's surface. Carbon dioxide is what you exhale with every breath. Organic molecules make up your body, your food, every living thing you have ever encountered. These chemicals are the ingredients of life. Not just on Earth, anywhere. If life exists elsewhere in the universe, it almost certainly requires these same building blocks, and SPHEREx is tracking them across thousands of light years. Here is why that matters. Stars do not form in isolation. They emerge from giant molecular clouds, vast regions of gas and dust drifting through space. These clouds contain everything needed to build solar systems. Hydrogen and helium dominate, but mixed in are heavier elements: carbon, oxygen, nitrogen, silicon, iron. And critically, complex molecules. Water ice coats dust grains. Carbon dioxide freezes in shadowed regions. Organic compounds, some containing dozens of atoms, float through the interstellar medium like seeds waiting to take root. When a star ignites, the leftover material forms a disk, a swirling plane of matter orbiting the newborn sun. Planets condense from this disk. Rocky worlds form close to the star where it is hot. Gas giants emerge farther out where it is cold. And the chemical composition of those planets depends entirely on what was present in the original cloud. If water ice was abundant, you get ocean worlds. If organic molecules were common, you get planets rich in carbon-based chemistry. The ingredients for life get baked into worlds during their formation. SPHEREx can see this process happening. In infrared, water ice has a distinctive spectral signature. It absorbs and emits light at specific wavelengths. Same with carbon dioxide, same with organic molecules. By observing stellar nurseries across 102 colours, SPHEREx identifies where these chemicals exist, how much is present, and how they move through space. It maps the distribution of life's ingredients across the galaxy. And in doing so, it answers a question humans have asked for millennia. Are the building blocks of biology common or rare? Are we the product of extraordinary luck, or is the universe primed for life? The data is already revealing patterns. Organic molecules are not confined to a few special regions. They are everywhere, drifting between stars, embedded in comets, coating dust grains in planetary nurseries. The chemistry of life is woven into the fabric of the cosmos itself. This does not prove that life is common, but it suggests that the raw materials are abundant. The universe is not hostile to biology. It is chemically prepared for it. But SPHEREx's legacy extends far beyond the search for life. The mission is also studying how galaxies evolve over nearly 14 billion years. Remember, distance equals time. When SPHEREx observes a galaxy 10 billion light-years away, it sees that galaxy as it existed 10 billion years ago, just a few billion years after the Big Bang. By mapping hundreds of millions of galaxies at different distances, the telescope constructs a timeline of cosmic evolution. It watches galaxies grow, merge, and transform across the entire history of the universe. This is not incremental science. This is watching the plot unfold. You see galaxies as they looked shortly after formation, small and irregular, blazing with star formation. You watch them collide and merge into larger structures. You observe how star formation rates change over billions of years. You trace the build-up of heavy elements as generations of stars live and die. You witness the universe maturing from chaos into the ordered structure we see today. And here is the remarkable thing. SPHEREx will complete 4 full all-sky surveys during its mission. 4 complete maps. Each one building on the previous. Each one going deeper, capturing fainter objects, refining measurements. Combining multiple scans increases sensitivity exponentially. Signals hidden in noise become clear. Patterns invisible in a single observation emerge when you stack data from repeated surveys. By mission's end, SPHEREx will have created the most comprehensive infrared portrait of the universe ever assembled. The mission is managed by NASA's Jet Propulsion Laboratory, the same institution that brought you Voyager, Curiosity, and countless other groundbreaking missions. Hardware was built by BAE Systems, leveraging decades of aerospace engineering expertise. Science teams span the United States, South Korea, and Taiwan, making this a truly international effort. Data processing and archiving happens at Caltech's Infrared Processing and Analysis Center, ensuring that every observation is preserved, calibrated, and made publicly available. That last point is critical. Publicly available. No institutional gatekeeping, no restricted access. Anyone can download SPHEREx data and explore the universe. High school students, amateur astronomers, researchers in developing nations. The democratization of cosmic knowledge. This is how science should work. This is how discoveries accelerate. When data flows freely, when minds from every background can engage with it, breakthroughs happen in unexpected places. And perhaps most importantly, SPHEREx will guide future missions. It is a pathfinder. When James Webb Space Telescope or future observatories need targets, they will consult SPHEREx maps. The mission tells them where to look. Which galaxies are most interesting? Which stellar nurseries contain unusual chemistry? Which regions of sky hide faint structures worth detailed study? SPHEREx provides the roadmap. Other missions follow the trail. SPHEREx has opened a door. But what lies beyond that door is even more extraordinary. Because NASA is not stopping here. The space agency has already begun planning missions that will push far beyond what SPHEREx can achieve. Missions designed to answer questions we could not even formulate a decade ago. Missions that will probe the observable universe with such precision that the boundaries between science and philosophy start to dissolve. And once you understand what is coming, you will realize that we are standing at the threshold of a revolution in human understanding. Let me start with a problem. SPHEREx maps the entire sky in 102 infrared colors. That is unprecedented. That is groundbreaking. But it is also just the beginning, because the observable universe is not a static photograph. It is a dynamic, evolving system stretching across 93 billion light-years. Yes, you heard that correctly. 93 billion light-years. Not 13.8 billion. The universe is 13.8 billion years old, but space itself has been expanding the entire time. Objects we see today have moved away from us as their light traveled toward Earth. The edge of the observable universe, the cosmic horizon beyond which we cannot see, is now 46.5 billion light-years away in every direction. That gives us a sphere 93 billion light-years across, and every cubic meter of that volume contains information. SPHEREx gives us a map, but NASA wants something more. It wants a simulation, a complete dynamic model of cosmic evolution from the Big Bang to the present day. Imagine a digital twin of the entire observable universe, every galaxy, every star cluster, every nebula, all traced through 13.8 billion years of history. You could rewind time and watch structure emerge from primordial chaos. You could fast forward and predict how galaxies will evolve over the next billion years. You could zoom into any region of space and see not just where objects are, but how they got there and where they are going. This is not science fiction. This is the goal of missions already in development. And the first step is called the Nancy Grace Roman Space Telescope. Roman is scheduled to launch in the next few years, and it represents a quantum leap beyond anything currently in orbit. The telescope has a field of view 100 times larger than Hubble. 100 times, that means it can survey vast regions of sky with the same resolution and sensitivity that Hubble uses on tiny patches. Roman will observe hundreds of millions of galaxies. It will measure their distances, their masses, their chemical compositions, their ages, and it will do this across cosmic time, watching galaxies evolve from infancy to maturity. But here is where things get interesting. Roman will focus heavily on dark energy. You have heard of dark matter, the invisible substance that makes up 85% of all matter in the universe. Dark energy is even stranger. It is the mysterious force causing the expansion of the universe to accelerate. Galaxies are not just moving apart. They are moving apart faster and faster. Something is pushing them. Something is overpowering gravity on cosmic scales. We call it dark energy, but that is just a label. We have no idea what it actually is. Roman will measure the distribution of galaxies across billions of light years with exquisite precision, and by analysing how that distribution changes over time, scientists can test theories of dark energy. Is it a cosmological constant, an unchanging property of space itself? Is it a dynamic field that varies over time? Is it evidence that our understanding of gravity breaks down on cosmic scales? Roman will provide answers, or at the very least, it will eliminate wrong ideas and point us toward truth. But NASA is not stopping with Roman. The next frontier is multi-messenger astronomy. This is the idea that we should observe the universe not just with light, but with every type of signal available. Gravitational waves, neutrinos, cosmic rays. Each one carries unique information. Gravitational waves ripple through space-time when black holes collide. Neutrinos stream out of supernovae, carrying energy that photons cannot escape. Cosmic rays are charged particles accelerated to near light speed by violent events we barely understand. Combining observations from multiple messengers allows us to reconstruct cosmic events with unprecedented completeness. NASA is developing missions that will detect gravitational waves from space. Ground-based detectors like LIGO have already proven the concept. They detected gravitational waves from merging black holes, confirming predictions Einstein made over a century ago. But ground-based detectors are limited. Seismic noise, atmospheric disturbances. Gravity itself creates noise that cannot be eliminated. Space changes everything. In orbit, detectors can be millions of kilometers apart. They can observe gravitational waves at frequencies impossible to detect on Earth. They can watch supermassive black holes merge at the centers of distant galaxies. They can trace gravitational wave backgrounds left over from the Big Bang itself. And then there is the ultimate goal. The mission that sounds like fantasy, but is already being designed. A space-based telescope capable of directly imaging Earth-like planets around nearby stars. Not just detecting them, imaging them, resolving surface features, measuring atmospheric composition, looking for biosignatures like oxygen, methane, and water vapor in combinations that indicate biological activity. This mission, currently called the Habitable Worlds Observatory, would answer the oldest question in human history. Are we alone? Imagine what that means. Imagine a photograph of a planet orbiting Alpha Centauri, 4.3 light-years away. Imagine spectroscopy revealing an atmosphere rich in oxygen and ozone, clear signatures of photosynthetic life. Imagine detecting seasonal variations in atmospheric chemistry, suggesting active ecosystems responding to climate cycles. You would not just know that life exists elsewhere. You would know what kind of life. You would know how common it is. You would know whether intelligence is rare or abundant. But here is the challenge. Imaging an Earth-like planet is absurdly difficult. The planet is tiny. It orbits close to a star billions of times brighter. The glare from that star drowns out the faint reflected light from the planet. It is like trying to see a firefly next to a searchlight from 1,000 kilometers away. Impossible with current technology. But NASA engineers are developing solutions. Star shades, coronagraphs, interferometry techniques that block starlight while preserving planetary signals. The technology is advancing, the mission is feasible, and when it launches, it will change everything. So here is the trajectory. SPHEREx maps the universe in infrared. Roman measures cosmic expansion and dark energy. Gravitational wave detectors probe space-time itself. And the Habitable Worlds Observatory searches for life. Each mission builds on the previous. Each one pushes the boundaries of what we thought possible. And together, they form a coherent strategy. Not just observing the universe, understanding it, not just collecting data, answering questions. The observable universe is not some abstract concept studied by academics in isolation from human concerns. It is the context of our existence. Everything that has ever happened, every atom in your body, every thought you have ever had, emerged from processes that began 13.8 billion years ago. Understanding those processes is understanding ourselves. Mapping the cosmos is mapping our origins, and the missions coming in the next 2 decades will complete that map with a thoroughness that previous generations could not have imagined. So ask yourself this: what would you do with complete knowledge of the observable universe? What questions would you ask? What mysteries would you pursue? Because those questions are no longer hypothetical. The tools to answer them are being built right now. The data is being collected, the analysis is underway, and the discoveries that emerge will define the next chapter of human civilization. We are no longer wondering about our place in the cosmos. We are measuring it, and nothing will ever be the same.